Hello, everyone. Thanks for coming to the Temporal Graph Reading Group today. We are very glad to have Julia today, who is one of our organizers presenting her recent work, comparing apples and oranges on the evaluation of methods for temporal graph forecasting. I think the paper title itself already have novelty. So on the apple and oranges, I'm just kidding. But so I will start with the speaker bio. So Julia Gastinger is a research scientist at NEC Laboratories Europe and a second-year PhD student in the Data and Web Science group at University of Mannheim, supervised by Professor Heiner Stockenschmidt. Sorry for the pronunciation. Her research primarily focused on temporal knowledge graphs. Specifically, she is interested in temporal knowledge graph forecasting and the evaluation of methods in this research field. Julia actively contributes to the research community as a co-organizer of the Temporal Graph Learning Reading Group. So we're very glad to have Julia today, and I'll hand the mic to you, Julia.
Thanks a lot for the kind introduction. And I'm gonna share my screen now. Can you see it?
Yes.
Okay, great. So, and you already introduced the paper title, Comparing Apples and Oranges on the Evaluation of Methods for Temporal Knowledge Graph Forecasting. And I did this together with my colleagues Timo, Lokesh, Annette, and my supervisor, Heiner Stockenschmidt. All right, maybe before we start, temporal knowledge graphs are knowledge graphs. So knowledge graphs, but with time information. So facts can occur, facts can recur, and facts can evolve over time. And what's important in this knowledge graph setting is that we have multi-relational data. So we have different types of relation that connect different types of nodes. And usually in static knowledge graphs, you represent the information with triples. For example, you have something like person A appeal for change in leadership for government country of X, as you can see, for example, here. And now if we have this temporal knowledge graph setting, we also have the time information. What people usually do in temporal knowledge graphs is we have discrete time representation. And then you can represent this temporal information by adding a timestamp. And then you extend those triples to have quadruples. For example, you would have person Z appeal for change in leadership for government country X with a timestamp like 2018. And then you can create knowledge graph snapshots. And one of those snapshots, for example, this one, represents all the triples that are known to be true at this timestamp. And then you have these equally sized or equal distance snapshots, and each of them has a set of triples. And that's how you can work with those knowledge graph snapshots. There's other ways to represent time there, but this is the way that the works that we analyzed used. And then this work focuses on knowledge graph forecasting. What is that? It's to extrapolate to future knowledge graphs based on a history of knowledge graphs. Typically, what people do is future link prediction. So a question could be like, I don't know, whom is Obama gonna visit in a future time step? Something like that. All right, so knowledge graph forecasting is the extrapolation to future knowledge graphs. What's the state here, or why are we doing this work? We've looked at the work that exists, and various methods have been proposed to advance the field of temporal knowledge graph forecasting. All of them are somewhat different. They are pretty cool ideas. However, when we looked at them more closely, we found that there are some discrepancies in the evaluation settings. And now our work addresses these issues in the evaluation of temporal knowledge graph forecasting methods. So in our work, we discussed the evaluation settings and the problems that we found for temporal knowledge graph forecasting. And we proposed some kind of unified evaluation protocol for the forecasting. And then we did a re-evaluation of state-of-the-art models. And yeah, we show results, of course, and we also show some insights on the influence of those different evaluation settings on the results. And this is also what this talk is going to be about. So I'm going to give a very short overview of state-of-the-art. I will talk about the problems that we found, about the evaluation protocol. I will show some experiment insights. I will describe the experiments, and I will also show some checklists that we came up with. And yeah, I'm going to end with limitations, a summary, and future work. And maybe a short notice, if you have any questions in between or any remarks, feel free to interrupt me anytime. All right, so this is just a very summarized overview of state of the art. Basically, you can group the methods that have been proposed. There is a group, for example, ReNet, REGCN, Tango, which work on graph neural networks, but combine them with some sequential approach. So you have the graph neural network to integrate the structural information, and then a sequential approach like a recurrent network or something like that to have the time process. And you combine both in a learning process. Then there are two works who use somewhat reinforcement learning, for example, or Cluster and Time Traveler. They use reinforcement learning to find paths for the agent to walk through the graph over time. There's a rule-based approach, which is called T-logic. This one learns temporal logic rules with some temporal random walks and walks through the edges through the graph backward in time. And then there is also another approach, which is called SciGNet, which predicts future facts based on the appearances on historical facts. So yeah, this is just a very short overview. If you want more information, I have added the references, and also in our paper, we have a bit more information. So now when we looked at these works, we found some discrepancies in the experimental settings. So this is the overview. It's 4 of those discrepancies, and I'm going to describe them now step by step. So the first one is that the existing models are evaluated on scores, but those scores are computed with different settings. So usually in temporal knowledge forecasting, or in the cases that we look at, one does entity prediction for future time steps. For example, one predicts what or whom will Obama visit in July 2023. And then also the other way around. For example, France, so who will visit France in 2023? And then one evaluates them by using metrics which are known from static link prediction for knowledge graphs, namely the mean reciprocal rank, the MRR, and the Hitzek K, with K being 1, 3, and 10. And now there are 3 settings. The first one is the raw setting, which is, I think, known to all knowledge graph people, but probably not known to the graph people, so I'm going to quickly explain it. So one looks at each triple on the test set, and then the model computes a score for each node in the knowledge graph to potentially belong to that triple from the query. And then those scores are sorted. Higher score means it's more likely to belong to that triple. And the set of all possible nodes or of all possible triples is called the corrupted triples. And then one sorts the scores in descending order and notes the ranks of the correct entity. And this is also repeated for the subject prediction. And now the MRR is the mean of the reciprocal of these ranks across all test queries. So far, so good. But then some people noticed that, well, actually there can be more than one valid prediction. For example, Obama could visit Italy and France, and both predictions would then be correct. But one only always looks at one test triple. And so the static filter setting wants to avoid counting higher ranks for other valid predictions as errors. And the proposal, or what's done in static filter setting, is to remove all the triples from the set of corrupted triples that also appear in a train, validation, and test set. And this works well for the static setting. However, now if we're in the time setting, it's kind of inappropriate because the static filter setting filters out all triples that have ever appeared from the corrupted triples, but it does not consider any time information. So for example, if Obama has visited Germany in 2013, and now we're in 2015 for the test query, then Obama visit Germany would still be considered as a valid prediction or not considered as an error, although it happened 2 years ago. So this is not really working for the time setting. And that's why the time-aware filter setting was proposed. This only filters out the quadruples with the same time step as the test query. So for example, Obama visits Germany would only be filtered out if it also happened in the same time step as the test query. So far, so good. Now we have 3 different filter settings. Actually, for our case, the time-aware filter setting works and the others are kind of not so appropriate. And the problem here is that the methods that we've looked at use different filter setting. So not all works report their results on all filter settings, which decreases the comparability. But also some works only report the results on the raw setting or on the static filter setting. And these settings are actually not really appropriate for the temporal knowledge graph forecasting. So this is the first problem. If you have any questions, just interrupt me, please. The next one is there's two settings, single step prediction and multi-step prediction. Single step prediction is if you predict one step into the future. For example, here you have all these observed values and predict one step to the future. Then you feed the ground truth and you predict another step to the future. So the model always has to only predict one step ahead. And then there's multi-step prediction, where the model has to predict all the test's future time steps at once without seeing any ground truth in between. And naturally, the multi-step prediction is more difficult because the model gets less information. And the farther you look into the future, the more difficult it gets. The problem here is that the models for single-step prediction are directly compared or lumped together with the models for multi-step prediction, which is a problem because it's unfair. So the state-of-the-art models run in different settings, and the single-step models are compared to multi-step models without drawing some kind of attention to the different setups. That's another problem. And the third problem is that multiple versions of the same data sets are used for evaluation. So this is just an overview of what kind of data sets are used, the names, and later I will also, for example, there's this data set ISWS14, and there are 3 versions of the same data set, all marked by the same name, but they have different number of triples, different number of nodes, for example. And one of those versions is especially problematic because it comes without a validation set. People who are using this one are using the test set for validation, which, well, it's test set leakage, so it's not a thing that one should do. And then if those papers report their results on different versions of the data sets, it makes also the results across the papers not comparable. Yeah, that's the third problem. And then the fourth problem is on the usage of the validation set during the testing. So some models do use the information from the validation set for testing, and others do not use it. This is a problem because it's just different usage of information. So if you use the validation set during testing, it means during testing, the model knows all the steps that have happened up until the last validation set. And if you do not use the validation set during testing, it means that there is this gap of unknown information before the model starts the testing. So it's just different ways of setting. That's a fourth problem. So not using the information from the validation set leads to a harder task as the model needs to forecast more steps into the future. And then there's this validation gap by the information gap by the validation set.
I think there's a question from the audience, Julia.
Ah, yeah, sure, feel free to ask. Or is it in the chat? Ah, I don't, here's the chat. Since knowledge graph is a graph, could you please explain the plots on slide 415, how to transform the knowledge graph into a one-dimensional signal? Ah, yeah, okay. Sorry for the confusion on slide 15. This is a normal time series. I just wanted to show how this is done for normal time series with the train, validation, and test set, because I didn't know a good way to represent the knowledge graphs in some one-dimensional signal. So this is a normal time series. Thanks for showing the point. This was a bit confusing probably. Okay, so this is clarified, Res. Yeah, you say thanks. Cool, thanks for pointing this out. Okay, so to sum this up, we have found 4 discrepancies in the experimental settings. I will just shortly repeat them. The first one, the models are evaluated on scores computed with different settings. The first one was this issue on multi-step and single-step prediction being compared to each other. The third one on the multiple versions of the same data sets. And the fourth one on this validation set usage or not usage. So this is a large table. We have it in our paper. You can look it up in our paper in detail. What I just want to show in this table is that among the 8 models that you can see here that we compare, and here you see the different settings, and among all of those models, no 2 models have been evaluated on the identical settings. So if you look at the papers, you can just not at all compare their tables because none of them are on the exact same settings. There's always something which is somewhat different. Which I think shows the need to re-evaluate it on like one protocol. So what we did is we defined this evaluation protocol to do it all on one kind of setting. So for the filter settings, we suggest to report the results on a time-aware filter setting because it avoids counting higher ranks from other valid predictions as errors, but it takes into account the time validity effects. Then for the single step and multi-step prediction, both settings are valid and it depends on the use case where you want to go, how many steps you want to predict or you need to predict. However, the models who can only do single step prediction should not directly compare the results to multi-step prediction because it's unfair. If a method can predict in both settings, we just re-evaluate it on both settings. On a dataset version, it makes sense to use the same dataset versions to compare the works to ensure comparability. In our evaluation, we just use the dataset versions that have been used among the most often. And then on the train validation and test set usage, the validation set can be used for testing to avoid the time gaps between training and testing. We chose the setting because this is also used when you do time series forecasting. You can also use the validation, the information from the validation set to testing. Some additional notes, it should be clear to not use the test set for model selection. And also the data sets should be split based on order timestamps, and one timestamp should not belong to two different sets. So for example, not the same in validation and test set. All right, so we have defined this or collected this evaluation protocol, and then we have re-evaluated the models. So we re-evaluated the 8 state-of-the-art models where code was available for future link prediction on 5 data sets. GDAL, Diago, Wiki, ICE14, and ICE18. And we report the aggregated results, the mean MRR and the hits at 1, 3, and 10 across all test samples. On the time-aware filter setting for single-step and multi-step prediction. And then we also have some figures where we show the MRR over snapshots per method to show the influence on the evaluation settings. And yeah, here's the GitHub link in case you want to look at the code or want to rerun the experiments or want to add a model or something. Yeah, so in the paper, we have this very, very large table. I guess you don't want to look at it in detail now. Maybe just some summarized insights. What you can see overall, the scores for multi-step setting on top here are in average lower than the scores for single step setting, which makes sense because single step setting, as I said, is easier. And also, a somewhat interesting finding is that there's no model which has the best results across all data sets. So we have marked the best models for each data set in bold, and you see that this kind of varies through the data sets. Yeah, these are just some summaries, and now I will show some figures to show or discuss a bit more. Yeah, there's a question, Andy.
Yes, for the multi-step, how far ahead in the future are you looking at?
This depends on the data set. So between 6 time steps for Yago and I think 30 something time steps for the ISWS 14 or 18.
So I think I think for simple step, it's not the hyperparameter of like how far away you can look into future, but I think for multi-step, it's something that's also like also hyperparameter, right? The further away in the future, the performance will degrade more. And also depending on the use case, it shows different performance. So
Yeah.
Yeah.
Yeah, you're right. It depends pretty much on the use case and on the data set. I mean, usually what is done with the data sets, you split this 80% training, 10% validation, 10% tests. And then the longer your data set is, the more days or months or whatever you have, the longer also the test set horizon is.
Mm-hmm.
But yeah, it depends also on your use case where you want to apply the model to. So yeah, you're right.
Yeah. Yeah. Now, do you think there's any problem with the data sets used for evaluation? So you talk about the evaluation setting itself,
Mm-hmm.
but are the data sets maybe also a bottleneck, or do you think that's an issue?
I think the data sets in general are pretty much all right, as far as I can tell. I've looked at them. How do they evolve over time? How do the nodes evolve over time and stuff like that? I think they are pretty much all right. Maybe something that is to be noted is that they are also quite different. For example, for ICE 14 and ICE 18, you have more some kind of events happening, like
Mm-hmm.
people attacking each other or people visiting each other. So this happens once and then it's gone. And then for, I think, Yaku or Wiki, for both, you have more interval kind of information. For example, people playing soccer at a different, for a certain team for an interval of time, which then takes place for some months and is repeated all over again. So this is maybe something to be noted when one makes a model, to see where is it good at, where should it be good at.
Do you think that would explain why the performance on Yago and Wiki is generally higher than all the other data sets?
Yeah, probably. Also because something like if you play for a soccer team today, you will also play for it for the next week or month to come. So this is a fact which is easy to be predicted, for example. So,
Right.
but yeah, it's just an assumption. I did not verify this per se, if this is the reason why it's easier or better performance.
And then for the GDAL data set, is it a large one or?
Yeah, it's very large.
Okay.
I have the data set statistics somewhere. Do you want to see them?
Sure, if you have them. Thanks.
Yes, let me quickly open the slide. 1 second. So it's a hidden slide. That's why I'm just going to show it like this. So GDALT has 1.7 million train triples, which is significantly more than the others. Can you see the slide?
Might be a little bit too hidden for us to see.
Too small. Wait, let me quickly. Yeah. Now you can read it, right?
Yes.
Okay,
yes.
yeah. So here you see it has a significantly higher number of triples.
The number of relations is significantly lower for Yago and Wiki.
Yeah, that's also true.
That could explain the performance-wise, and the duration for the ICEW is very, very small in like temporal graph standard, like 24-hour. You could have many.
This means one time step means 24 hours. So in total, these data sets are 1 year. So the 2014 is ICE 14.
Okay.
And then you have one snapshot per day. And for GDALT, you have one snapshot per 15 minutes.
I see. Okay, so that's the time granularity. Okay, I see.
Exactly.
17 million edges. No, that's
1.7
yeah, that's just 1.7 million.
Yeah.
Still relatively small size, kind of similar to standard temporal graph learning, like standard like homogeneous graph prediction.
I actually have not really an intuition on that because I never work with non-knowledge graphs. Yeah.
Right. Yeah, okay. Sounds good. Thanks.
Welcome. Okay, so I will now show some figures which somewhat show the effect of different settings. Where's my mouse? Here it is. So this one shows actually pretty much what we just discussed on the multi-step and single-step setting. So here you see one of those figures per data set, per setting. So on top you see the ICE WS18 for multi-step and single-step. and the wiki for multi-step and single step. And here you have the MRR for one entry per snapshot from the see basically is that for multi-step, there is a decreasing trend over time. The farther you go into the future, the lower in average the MRR gets. For single step, the trend is not the case. And you can also see the same for wiki. So the farther you go, the lower it gets in average or in overall. So yeah, this result just actually reflects the statement that multi-step prediction is more challenges and that the uncertainty accumulates across time or with increasing time steps. So yeah, I think this just re-shows the fact that one should not compare the multi-step prediction models to the single-step prediction models. Only for the first time step, there it is the same setting for both.
That makes sense.
Yeah.
And if the number of steps goes to infinity, the performance should go to 0, right?
Yeah.
Intuitively.
I would expect so. Maybe there is some kind of seasonal behavior, like the same things, really same things happen again every week. Then it would probably not be the case. Yeah.
I think that makes sense. Thanks.
Okay. And yeah, okay, this is just a summary. Told that already. This one is showing the effect of using the validation set versus not using it. This is for the two methods, T-logic and SciGNet, because they are both in their original experiments not using the validation set. So what you see is, here is the difference. So when you use the validation set here in this dark green, and versus when you not use the validation set, you have a pretty high performance increase. For T-logic, this is very understandable, or yeah, because T-logic, it makes those rules by walking through time. It says something like, if I go to Italy today, I will go to Spain tomorrow. So now if you have this gap in information, you lose this for making your rules, which makes it way more, or the rules way less reasonable. This explains, I think, a bit why for T-logic there's this very high increase in performance. But also for SciGNet, it's a rather high increase. And we've seen this increase for most of the data, or for all of the data sets. For wiki, the number of validation samples is 11, as far as I remember. So the information gap would be 11 time steps. Yeah. And then here we have a figure which shows the effect of the three filter settings on the MRR. I have this example for two methods because otherwise the figure would be too crowded. So you see SciGNet in gray and static, and then the other two colors here in raw and time aware, and RGCN here in static, and also here in time aware and raw. And also here we see a very high, actually, MRR distance for the same method on the same data set between the static filter setting and the time aware or raw filter setting. SciGNet, I said this in the beginning a bit, SciGNet is trained based on kind of repeating historic facts. It's a bit more complicated, but what it does, it learns to re-predict historic facts. So when it's evaluated in a static filter setting, the repetition of facts from the past is not considered as an error. That's why it gets super good results when you evaluate it on a static filter setting. But the results are actually much worse when you evaluate it on the time aware or raw filter setting. So I think that's also a very important takeaway, that one cannot so much trust the static filter setting, or one should for sure not compare the numbers from the static filter setting with the other filter settings. Yeah, I think, yeah, these are the main takeaways that I wanted to show in figures. This is just a summary. First thing, no model shows the best results across all data sets. So there's no one model which is the best. So I think this just marks the importance of fairly comparing the models on different benchmarks, or on saying, okay, our model is specialized in this and that. That's why we just have these data sets. And we showed some clear differences in the result scores for single step and multi-step prediction, for the usage of validation set or not usage, and for the influence of the filter settings that are used for computing the scores. And this is something that I wanted to show in case any of you also want to conduct some experiments on that. This is just a checklist that helped me to do those data sets. Whenever I added a new method, I would go through those points. So the first one is make sure to check that the data sets are used, that the data sets are used are the same for all models. One can check the number of triples, number of nodes, the number of time steps, because sometimes it's just not visible when you just see the name. Then are the hyperparameters that you run your experiments with the same as the ones reported in the papers, because sometimes the default parameters in the code are not the same as the ones that are reported in the papers. Another thing is the single step and multi-step setting consistent across all models. Is the validation set used during testing? This is also something to be checked in the code. Are you sure that the test set is not leaked during the training? Does the model predict in both directions, predicting the object and predicting the subject? Are the evaluation score computed based on the time array filter setting? And is the implementation to compute the evaluation scores, the MRR and so on, consistent across all models? I mean, I think there are potentially more things to check, but these points help me. So maybe they also help you at some point. And yeah, this is just a short summary. Are there questions in the chat? Sorry.
Yes, there was a question in the chat. And nice checklist, by the way.
Thanks. Could you please explain the meaning of the x-axis in slide 25? Is that sample index? Sorry, I'm going to go back. So yes, this is the ID of the snapshot from the test set. So yeah, there are, for example, 300 test set samples for GDELT because you have so many time steps for GDELT because you have this 15-minute interval. So each of the entries is one graph snapshot from the test set. I hope this clarifies your question. Yeah, if it doesn't, then please just interrupt me or just write in the chat again. Okay, so I'm gonna quickly repeat the evaluation protocol. Just a summary: filter settings, time-aware filter setting is the way to go. To never compare the scores from single step and multi-step, although both settings are valid depending on the use case. Check the dataset versions, and we said that the validation set can be used during testing to avoid the time gaps. Then I wanted to mention this limitation that we have. Usually it's better to do multiple repetition for each experiment run. So for each data set, for each method, for each setting. However, we could not do this because we had super significant computation times for many models. For example, for the GDELT data set, we had for some models multiple weeks to train, and yeah, we just couldn't repeat multiple times. However, what we did is we checked our results when they were comparable to the results in the original papers, and we noted in a table if there were some differences in the scores, and usually it were very small differences. So this is something that one can check in the supplementary material. But of course, doing multiple repetitions, it would increase how good the robustness of the results. Yeah. And then I wanted to give a short summary. I think you know it by now. This paper is on the evaluation of temporal knowledge graph forecasting models. We described the inconsistencies. We have this unified evaluation protocol and re-evaluated the state-of-the-art methods. And what we actually aim at with our work is to have this unified evaluation protocol for future work to be evaluated on that, so we can directly compare the results, and also to somewhat stimulate discussions on the evaluation and also raise the awareness that it's better to check sometimes the experimental issues or results. Yeah, with the hope that this advances the research field of temporal knowledge graph forecasting. We have made some suggestions actually of how we could extend the evaluation of temporal knowledge graph forecasting models. So first one is some of those models, they, for example, ReNet, they can not only do future link prediction, but they predict full future graphs. So they would, for example, predict for future time steps the 1,000 most likely triples. So an idea would be to evaluate the full predicted graph. We have not had any concrete idea, but maybe something based on graph similarity or by computing a percentage of correctly predicted triples, because this is actually a quite useful strength of ReNet, but nobody has evaluated it. Another thing would be to evaluate the change of the predicted graph snapshots over time. So to check, does the model actually always predict the same for the future time steps, or do those predictions really change in the future? To see if they evolve and if they are able to somewhat capture the time information. What we could do would be to compare the predictions at different future time steps. This is also something, to the best of our knowledge, nobody has done and might be useful also when checking how to improve the methods. And then another thing is to include a more fine-grained evaluation to answer what properties the models learn and what they did not. For example, by breaking down the MRR over individual data subsets. There are some tools done for static knowledge graphs. For example, there is a thing called, I think, knowledge graph box, where you can, for example, enter certain relation IDs, or you distribute the MRRs based on certain settings and then evaluate where is the knowledge graph forecasting good at and where are some things to be improved upon. So yeah, I'm not sure if anybody of you has worked in this direction and has some experiences or ideas or an opinion on this. I'm happy to talk about this more. Yeah, and that's actually it from my side. So yeah, if you have questions, ask them either now, send me an email, write in our Slack, check out the GitHub repo. Here are also the references, yay. They are more readable in our paper, of course. So yeah, just read the paper if you want to read the references in detail, I guess. That's it from my side. Does anybody have any questions?
Thanks for the great presentation, Julia. So I do have some questions and discussion, but we can leave it to the end. And does anybody else have more questions or discussion? Feel free to unmute yourself or type the question in the chat, and so on. Okay. So I guess I can ask my question first, while people are thinking. So I think touching upon the point that you were discussing, Julia, about the repetition of events and like periodicity, and you mentioned that all data sets last at most a year, right?
No, TDELT is longer, I think. And Yago and Wiki are also younger because they have yearly intervals. So they are over several years.
Okay. But they don't have that many timestamps, right? So they have.
Yeah, I think, no, they don't have that many timestamps.
I see.
I can check it later, and I don't know it by heart.
Right, because like, for example, if you have some sort of seasonality repetitions, if you have a yearly snapshot, then you don't really see it because it's aggregated into the entire year, right? So you're not able to say in autumn this festival happens again, right, or something like this. I think there's like a bit. It could be interesting direction to see how does the models actually run over long periods of time with fine-grained time information.
Yeah, that's a very good point. And we know in ISWS 14 and ISWS 18, there is, for example, I looked at the number of triples or nodes per time step to check if there is some kind of seasonality. And we found that there's, for example, seasonality when it comes to the number of nodes, a weekly seasonality. So you have less nodes or less triples, both actually, on Sundays. That's an interesting thing.
Yeah, I think definitely interesting to investigate the data sets a bit more. Yeah, and also I feel like the data sets could also be larger scale. So similar vein to what I was talking about before, like if they have spent maybe across more years and then having more nodes and so on. But I don't know if there's actual raw data on those, or these are just the actual available data set. Like sometimes you have the data out there, but just not being collected.
So again, I mostly know for ICE-WS, it's Integrated Crisis Early Warning. This is based on this crisis database. So the raw data is actually available for each year. Yeah, so this is actually something that could be done, you're right. However, maybe a note on the larger data sets. So I've said for the GDELT, which is the largest data set, some of the models already needed weeks for training. So
Yeah.
I think there should first be some work on scalability potentially before people can use larger data sets.
But it's kind of chicken and egg problem. If you have a large
right.
data set, then it's easier to develop a method, because otherwise, even taking weeks, it's not that difficult for machine learning.
Yeah,
like
you're
you
right.
can run a thing for a week, but if you have something that takes half a year to run, then you have to have scalability, right?
Yeah, that's true.
But I think there's a lot of interesting direction there, and happy to discuss more, I guess offline. Yeah, does anybody else have some questions?
Thanks a lot for the great presentation. I just had one question about the future work. Have you ever tried anything at the first idea that you mentioned, predicting the whole graph at a time?
No, I haven't tried it. I would be very interested, but I haven't tried it myself yet.
Yeah, that's very interesting.
I'm not sure, are there knowledge graph forecasting people in this talk right now? Has any of you tried it? Then let us know. Probably not, because then people would have said something now. I guess that's
maybe
enough.
we will have comments in the YouTube video.
Yeah, let's see that.
Who knows? But I think it's a very interesting talk. Thanks, Julia. So actually, a lot of the things we have a lot of the exact same problems for standard temporal graph, like just link prediction as well. So I think a lot of the problems, like the temporalness of the evaluation, like doing the correct filtering, using the correct metric, standardized evaluation, and also standardize the settings. So I think this could be interesting. But I think the data set sizes could also be a limitation. So I think still currently it's only a few million. So I've seen in the TGL paper, there's a large temporal knowledge graph data set, but I don't know if I remember correctly.
Yeah, I think this is the GDLE.
So yeah, because I remember that one was very large, right?
Yeah.
It's like 350 million or something.
Yes.
So
I think it was in the order.
This one here would be a subset of that. Yeah. But regardless, if these methods already take weeks, so then
yeah, but it would be a good motivation to have the data sets to see that the methods also can perform on them. Yeah.
Well, think about it. If the method takes weeks to predict for now, then if you have a large scale data set, it might already pass the time in the test set by the time you actually predicted the test set.
That's
the
true.
running time would be years or something. So definitely scalability, I think, is a huge challenge in temporal graph in general.
Yeah.
Okay. So if there's no more questions from the audience, and feel free to send Julia about the questions, or you can forward it to me, or just connect on the Slack. And yeah, so thanks for everyone for coming to the talk today, and thanks for Julia for the very nice and very clean presentation.
Thank you.
And yeah, thanks everyone, and have a nice Thursday and morning, afternoon, or evening. See you.
Thank you.
Thank you.
Bye.
Thank you for the presentation.
Bye.
Thank you.
Thank
Bye.
you. Bye.